Hello again. We have defined a probability space and some nomenclature, and we'll have some examples and we'll proceed on the same time. Particularly in this video, we'll discuss the concept of continuous sample space and intervals. So let us consider a random number x between 0 and 1. This could be a time instance that somebody make a phone call to you today. Suppose that he will or she will do that. So this could be the time instance of something happening. The set of all numbers between 0 and 1, if I say that these are all equally likely to happen, so your outcome is somewhere in this area. It could be in an interval of between 0 and 1, so it could be here or it could be here. So but these two distinct points, they have equally likely probabilities. So we define our L as the set of all these numbers between 0 to 1. Now, how we could define the probability of an event? Suppose that you have an event A, which is the set of all numbers between a small a and a small b. So one definition, which is the definition to have equally likely for all points, is to say the probability of A is the probability of the size of A or length of A divided by the total length. So this is equal to the ratio of the size, or how big is size of A, or length of A divided by the size of L. So this is the relative size. This is the relative length of them. So obviously, using this definition, I could verify that probability of L itself is using that. If I replace A by L, it will become probability of size of L divided by size of L by size of L, and this is equal to 1. And you could verify that other properties of required in a probability measure is satisfied. So each outcome any countable set of outcomes has a zero probability. For instance, if I say that A is a set of just one number x, okay, then probability of A becomes equal to the size of A, and if I consider this one divided by L, by size of L is going to be 0 divided by 1 and is equal to 0. So if you have any set of countable points, then the probability becomes 0, because the length of a zero interval, because a single point doesn't have any length. So this is called a Lebesgue measure of a set, how the length from A to B is B minus A, this guy is... So non-zero probabilities are assigned to intervals of our line, not to outcomes. So every individual outcome has very tiny probabilities, which is 0. Another example, suppose that you toss a coin and then either you have head or tail, and then you could say that probability of receiving head. You remember that probability is only defined for an event. Here you could have an event. An event is a set, so you should have something, and here I have head. So if I write probability of head, that means that this is not meaningful, not defined, because head is not a set, but the set containing head is oh, this should be tail. Okay, is the probability of head is P, probability of tail is equal to 1 minus P, and P shall be between 0 and 1. So as soon as you say these, your probability measure is defined, and the triplets L, F, and P is well defined. Another example could be that you toss a coin 3 times. In that case, you will get your outcomes are in the form of either head, 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 or head, head, tail, or etc. So you have 8 possible outcomes, and you could assign probabilities to each individual case. The third example is that the L could be the set of intervals, the set of numbers in the interval between 0 and 1, and F includes all intervals of these 4. In this case, we call it a Borel field over the interval of 0, 1, and the probability of any interval, we define it length of I. So this is Lebesgue measure. So this gives you a valid probability space. So a coin, you could another example, you could toss a coin till you get your first head. So if your first head appears in the first attempt, you stop. But if tail appears, you need to repeat, and then you get another head. If in the second attempt you get head, you stop. Otherwise, you need to repeat. So your outcomes could be either head, or it could be tail and head, or it could be tail, tail and head, or it could be etc. So this is twice failure, or it's 1 success. It could be 5 times failure and 1 success. So in this case, because this is countable, I could use the power set as my sigma algebra. And I could, instead of defining my L like that, I could say L is equal 1, 2, 3, etc. And this L is the number of attempts. And so it's going to be same probability space, but different notation for L. For finite spaces, when L contains at most some number of fixed points, in that case, you could define your L as some your L becomes L1, L2, and let's say Ln. In that case, you could define probability of sets of the form Li, and you could say this is equal to Pi. So if PI's are non-negative, and then also sum of PI's is equal 1, you will get a probability space. So in that case, what you need, we need to specify this one. Our sigma algebra could be this one, and some of these guys should be equal to 1, and all of them should be non-negative. In that case, for any other event, A, because you could write A equals to union of some sets like Li's, for those Li's which are inside L, and these guys are disjoint, so from additivity property, you could calculate probability of A. So this method works for finite and perhaps countable L, but if L is not countable, then this may not necessarily work. So for that case, this is why we define a Borel field for real set, and we say that any member of Borel field can be decomposed into union of countable intervals, and therefore we could use the same similar principle. So this is why we needed to learn the sigma algebra. So if L is not countable, this method is not working, but if any countable L, this is working. For uncountable L, we consider our sigma algebra to be a Borel field such that any member of F could be written, A could be written as union of some intervals I, and I equal to 0 to plus infinity. But because these are countable, and then if there is no intersection between them, so we could say that probability of A is equal to probability of the intervals or the Borel components, and then summation of these one. Okay, and then we can calculate. And because you define these one well, then the probability measure is also defined.